Yeah, so today, Jonathan Gorard, hopefully I pronounced your name correctly.
Perfect.
Is giving a talk on towards formal correspondence between the Wolfram model and the ZX-Calculus.
Yeah, I guess first things first, I should try and explain exactly what that means. But so first of all, thank you so much to Cole and Bob and Hani and everyone else for kind of organizing this and inviting me along to it. It's a great pleasure to be with you. And I must confess, I feel a little bit inadequate, given that the extent of my formal training in category theory is one part 3 course that I took a few years ago. It was taught by P.T. Johnston, and although it was good, I'm definitely not a category theorist. But hopefully I won't say anything too embarrassing. The basic context is, so we, for a little while now, there's a group of us who've been investigating a discrete model of space-time, similar to things like causal set theory, for those of you who know about that, that's based on essentially hypergraph transformation dynamics, so based on defining abstract rewriting systems over hypergraphs. It's in effect, you can kind of think of it as being akin to an algorithmic variant of causal set theory. This model is known as the Wolfram model, and we've been increasingly interested in kind of this more general question of what is the connection between diagrammatic rewriting systems over combinatorial structures and the foundations of physics, which kind of very naturally led us to become interested in categorical QM and in the ZX calculus in particular. And I'm quite pleased to say that recently we've been able to use a bunch of ideas from ZX to sort of obtain a deeper understanding of our own sort of formulation of quantum mechanics in the context of this model. And I'm hoping that this is kind of the beginning of essentially a sort of mutually beneficial and symbiotic relationship between these two approaches. So we've certainly benefited from all the work that you guys have done on developing ZX calculus and all the kind of techniques that have gone in, that have sort of come out of that research program. But we're also somewhat optimistically hoping that some of the things that we've been investigating might potentially be of interest to you. I make no promises, but we'll see whether or not that's the case. So I'd like to begin, if I may, but just by kind of giving a brief summary of the context and the setup before going into further detail about how exactly it relates to the foundations of the ZX calculus. And before I do that, I should just quickly mention that the original work that I'm presenting here was done in collaboration with Množina Namadori and Xerxes Asawala. Xerxes, I believe, is at least tangentially known to this group. As the name suggests, the Wolfram model was not developed by us. It has its original conception with Stephen Wolfram, and subsequently several people, including myself and several others, have sort of worked on refining and extending it in various ways. Okay, so the basic setup, as I say, is we consider sort of hypergraphs, so generalizations of ordinary graphs in which edges connect arbitrary non-empty subsets of vertices, as being kind of our underlying spatial structure that we're operating on. There's no particularly fundamental reason for choosing hypergraphs over any other kind of combinatorial structure. The only real reason is they're a very kind of minimal sort of construct. I mean, you can just represent them as being collections of ordered relations between elements, as shown down here. And also because they come equipped with a kind of natural topological structure and indeed a natural discrete metric, that does come in useful later on when we start making considerations about general relativity and things like that. Okay, so effectively hypergraphs define the kinematics of our systems, and then the dynamics are defined in terms of abstract rewriting rules defined over hypergraphs. So we have an abstract rewriting system in which the objects are all hypergraphs, and in which the binary rewrite relation is such that if hypergraphs H1 and H2 are related, then or if hypergraphs G and H are related by the rewriting relation, then there's effectively a single application of that rewriting rule that transforms hypergraph G to hypergraph H, or formulated in terms of set substitution systems. You're basically saying that there is a subset of your collection of ordered relations between elements matching a particular pattern that can be replaced with a different subset matching a different pattern. So here's an example of a hypergraph transformation rule of that kind. And so then, starting from some very simple hypergraph, you can apply these transformation rules and you build up progressively more complicated looking things. So here's an example of starting from a single vertex with a sort of double self loop initial condition. And with this particular set substitution rule, this is the evolution trajectory you get, or at least I should say it's one evolution trajectory that you would get. And you've probably already preempted the fact that these questions about what is the correct evolution order, what is the correct evaluation strategy. These are kind of important questions with these kinds of formalisms, and I'll address those in more detail in a minute. And then after 14 steps of evolution, you get something like this. And very, very loosely speaking, the basic idea is that, once these hypergraphs become extremely large, they sort of resemble a continuous spatial structure in much the same way as, a large collection of discrete molecules resembles a continuous fluid or something like that. So to make the connection with physics kind of a little bit more tangible, what we can start to do is consider causal relationships between these updates, or between the rewritings. So each time a rewrite rule gets applied, we call that an update event. And the statement that I made earlier about how there are these different kind of possible evolution orders, different evaluation strategies on these hypergraphs, really corresponds to the statement that these update events don't occur independently of each other, that sometimes a pair of updating events will make use of the same collection of hyperedges. They will overlap with each other and therefore produce a critical pair in the associated abstract rewriting system. And other times, it would be the case that one updating event depends on a previous updating event having already been applied. And the way you can, so in that particular instance, it's kind of meaningful to say that one of those events is causally dependent on the other event. And so we can characterize that in terms of this combinatorial object that we call a causal network, which is just a directed acyclic graph in which all the vertices are just particular update events, and in which you have a directed edge connecting event A to event B, if and only if event B could only have been applied if event A had previously been applied. And sort of pragmatically, the way that we work that out is we look at which hyperedges does event B use as its input, which hyperedges does event A produce as its output, and if there's a non-trivial intersection between those sets, then you can say there's a causal dependence because B is making use of hyperedges that were produced by the output of event A. And as I say, the connection with physics, and in particular with causal set theory, lies in the fact that if we take one of these causal networks and we compute its transitive reduction graph, what you get is the Hasse diagram for some partial order relation. And in fact, in a certain class of cases, it's a partial order relation that approximates the causal partial order relation on a Lorentzian manifold. Or in other words, there's a certain class of these causal networks, which I'll define in a moment, which we know can be faithfully embedded into a Lorentzian manifold in such a way as to preserve its conformal structure. And so the idea is that these causal networks are therefore a reasonable candidate for a kind of underlying discrete model of spacetime. And because they're based on these hypergraph transformation rules, they're generated completely algorithmically, unlike in sort of causal set theory, where you have sort of stochastic underlying dynamics. So here's an example of a simple causal network for the set substitution system I showed before. We'll see some more complicated examples in a minute. So one question, the question that I asked earlier about how do you know in which order to apply the rules, how do you know which evolution history to pick, is really the question related to the question of how do we know that the causal network is always going to be unique? If we applied the events in a different order, how do we know we'd see the same causal network? Well, of course we don't in general. Because of the fact that we don't, the evolution of one of these hypergraph systems isn't just a straight path. What you actually, that picture I showed before was kind of an idealization, a fiction. What the reality is that you will actually get a directed acyclic graph, which we call a multi-way evolution graph, in which every hypergraph or every state of the system is a particular vertex, and an edge connects two states if one can be directly transformed into the other. So one of these multi-way evolution graphs is really just a very concrete way of thinking about the abstract rewriting structure. I mean, that's all that it really is, right? So what you're doing is you're saying, if two objects in my abstract rewriting system are related by the rewrite relation, then I can draw a directed edge between the associated vertices. And if there is a path, and moreover, sorry, if they are related by the reflexive transitive closure, arrow star, of the rewrite relation, then there exists a directed path between the associated vertices. So that's essentially what's going on. And then in that case, the particular evolution order that I showed before just corresponds to a particular path through this multi-way evolution graph. Whereas in reality, we could have picked any other possible evolution order, and we would have ended up with a different path with a different, potentially non-isomorphic sequence of hypergraphs. And it's kind of obvious. I should mention that the merging criterion for vertices in these graphs is based on hypergraph isomorphism. Okay, so I asked before, how can we guarantee that the causal network is actually unique? Well, in general, we can't, but it turns out that there's an important class of these systems, which we call causal invariant systems, for which the causal network is always the same. In other words, if you followed all possible paths through the multi-way evolution graph, the causal networks that you would see would all eventually become isomorphic as directed acyclic graphs. We call it causal invariance because what you're basically saying is that the causal network is invariant under parameterized changes of the updating order. So this is related, although not equivalent, to the global confluence of the underlying abstract rewriting system. And if you care about the details, then in the particular case where your system is not strongly normalizing, and therefore in which the rewrite relation is not well founded, and so Newman's lemma doesn't hold, it turns out you can prove inductively that global confluence is a necessary but not sufficient condition for causal invariance. And the reason we care about causal invariance from a physics point of view is that essentially, because this causal network is meant to be reflecting the causal structure of space-time, and because there is a one-to-one correspondence between different evolution orders and different choices of space-like hypersurfaces in space-time, as I'll show you in a minute, what you're saying by saying that the system is causal invariant is that the ordering of time-like and light-like separated events, which are the ones that are connected by causal edges, that ordering is invariant under parameterized changes of space-time foliation, even though the ordering of space-like separated events, i.e. the ones that are not connected that form antichains in the associated partial order, is not invariant. And so in particular, causal invariance allows us in certain limiting cases to prove essentially Lorentz symmetry of the limiting manifold. And as I say, that realization follows from the fact that there's this correspondence between foliations of the causal network into space-like hypersurfaces and different choices of updating order. And we'll see how that works in just a second. So here's an example of a sort of simple multi-way evolution causal graph. That is, so this is where we're overlaying the abstract rewriting structure and the causal structure on top of each other. So here we have state vertices that are shown in blue, showing individual states of the hypergraph. We have event vertices shown in yellow, showing the actual rewriting events. And then the evolution edges, which show which hypergraphs evolve to which other ones, are shown in gray, and the causal relationships between the updating events are shown in orange. And so here you can see, just by tracing through explicitly each possible path, that the causal networks you see, the pattern of relationships between the updating events is always the same. In fact, in this case, it's always a path graph. Okay, so when we pick a different updating order, what we're basically doing is, to evolve from kind of one generation of the hypergraph to the next generation of the hypergraph, what you're essentially doing is you're picking some maximal set of completely separated updates, so some maximal set of space-like separated updates, where the actual, where the inputs for the rules don't overlap with each other and therefore don't produce ambiguities. But for any given hypergraph, there will in general be many different possible sets of maximally space-like separated events. So in other words, there are different choices of which updating events you can consider to be simultaneous. And the point is that each such choice is effectively foliating foliating space-time, foliating the causal network into a different collection of space-like hypersurfaces, and is therefore corresponding to essentially to a different choice of reference frame. So here's a causal network for this simple hypergraph system. This is the particular evolution history that you get if you just perform the default foliation. You just foliate it flat like this, that you can think of as being like the the reference frame that corresponds to an observer at rest or something. But then we could also have picked this different evolution order, a different evaluation strategy, in which you can see that the sequence of hypergraphs is different. The sequences, these hypergraphs are not isomorphic to the ones in the previous picture. And you can see it's associated with this kind of bizarre, sort of arbitrarily curved, potentially sort of gravitational type reference frame. But the point is that even though the individual updating orders are different, and even though the hypergraphs that you see under these different evaluation strategies are different, because this system is causal invariant, it guarantees that under parameterized changes of foliation, the causal network, the causal structure is always preserved. And because, for reasons that I won't go into now, but I'm happy to talk about if people are interested, because these parameterized changes of foliations can be showed to correspond to conformal transformations of space-time, Causal invariance corresponds to the statement that the causal network is invariant under the action of the conformal group. And so because both the Lorentz and Poincare groups are subgroups of the conformal group, you can recover, with a bit of additional work, you can essentially recover all of special and general relativity from the assumption of causal invariance, plus some other assumptions. And I'm just going to quickly go into a little bit of detail about what I mean by a foliation, because it will come up later in the context of the stuff we're talking about with quantum mechanics and ZX. So when I say that we're foliating the causal network into this family of space-like hypersurfaces, what I really mean is that we're defining a function, which I'm going to call T, which is a universal time function that is mapping events, vertices in the causal network onto integers that correspond to which of these discrete time slices those events lie on. And then the statement that we, in such a way that the level surfaces of that universal time function are the space-like hypersurfaces, are the hypersurfaces in which every pair of events is space-like separated and therefore not connected by causal edges in the causal network. And the statement that we can do this, the statement that we can define a universal time function over that causal network that foliates it into a family of non-intersecting, non-overlapping space-like hypersurfaces corresponds to the statement that the associated Lorentzian manifold, the Lorentzian manifold in which the network can be embedded, is globally hyperbolic. And as I say, we'll see an analogous instance of this kind of idea in the context of quantum evolution in a moment. So just quickly before I move on to that, just to give you a sort of hint of how you get kind of limiting geometry and how things like general relativity start to emerge from these kinds of systems. If you look at something like this, so here's an example of a hypergraph system that produces a provably manifold-like hypergraph, a hypergraph whose structure limits to that of a Riemannian manifold, and therefore whose causal network limits to that of a Lorentzian manifold. You can start to compute sort of geometrical quantities, particularly things relating to dimension and curvature. So essentially the way you do that is, in the hypergraph case, is you can just, if you want to figure out sort of how many dimensions of space is your hypergraph corresponding to, you can just pick a particular node in that hypergraph, and then you can look at all the nodes that are adjacent to that node, and then all the nodes that are adjacent to those nodes, and so on, and you grow out some finite ball of radius r. And obviously, if the hypergraph corresponds to a d-dimensional space, you expect the number of nodes to grow like r to the d, which in fact it will do if that space is flat, is asymptotically flat. If it's curved, then there's a correction factor, which up to second order you can show is proportional to this quantity called the Olivier-Ricci scalar, which is a kind of discrete version of the Ricci scalar curvature that's known to limit to the ordinary Ricci scalar in the case where the hypergraph has a sensible limit to a Riemannian manifold. And you can do the same thing in the causal network too, although it's a little bit more complicated, right? Because it's a directed graph and therefore is a Lorentzian manifold. So instead of growing out a ball, you grow out some space-time cone that's projected in a particular direction. And you can look at how the volume of that cone scales. And again, what you see is a relationship like this, where you expect it to grow like t to the d if you're in a d-dimensional spacetime, and if it's curved, then there's a second order correction factor that now is proportional to a projection of the Olivier-Ricci curvature tensor, which in the time-like direction in which you've projected that space-time cone. And so it turns out, therefore, that, and down here, I've shown an example of these manifolds happen to be, this is a Riemannian and Lorentzian manifold, or a discrete version of them that happen to be asymptotically flat. Here's a hypergraph and a causal network corresponding to hyperbolic, sort of globally negatively curved manifolds, but using essentially similar rules. And so therefore it follows that in the continuum limit, if you want your hypergraph and your causal network to converge to sensible Riemannian and Lorentzian manifolds with finite dimensions, then that places certain conditions on the Ricci tensor. And in the most general case, you can compute what those conditions are, and they turn out to be exactly the Einstein equations. Essentially, you can deduce that by formulating the finite dimensionality requirement as an action principle, and then what you recover is essentially the Einstein-Hilbert action. But anyway, I'm not going to talk too much about that. This is just kind of trying to give you some of the setup of what it is that we're doing, and why it is that we're investigating this kind of algorithmic approach to doing causal set theory for generating discrete models of space-time. Just quickly before I move on to the connection to ZX-Calculus, let me first say something that's probably extremely obvious to this group, which is that at least in the case where our rules are reversible, although I've expressed everything here set theoretically, it's of course completely possible to express all of this in terms of adhesive categories and double push-out rewriting systems. And in fact, this will become extremely useful later for some of the theorems that I'm going to show later on. So as you all know, in the case of either a graph or a hypergraph, you can represent a symmetric rewriting rule L goes to R in the form of a span of monomorphisms of this kind, such that in our Wolfram model case, what we would say is that an updating event exists, an updating event can be applied if and only if this particular pair of push-out diagrams exists. This sort of formulation of the model in terms of adhesive categories, and particularly in terms of selective adhesive functors, this notion due to Kissinger and Dixon, will come in useful later on. Okay, so now that's sort of a load of stuff relating to the kind of relativistic side of this formalism, which is sort of, I have to say, much better worked out than the quantum mechanical side. But we have some conjectures about how sort of quantum mechanics works, in the context of these models. So the basic idea is that if you think about one of these multi-way systems, and you start to think of the observer not as occupying kind of a single path, but as being extended through multiple paths in the multi-way evolution graph, then the observer is effectively foliating the multi-way evolution graph into not space-like hypersurfaces, but rather these things that we call branch-like hypersurfaces, but which nevertheless behave in basically the same way. They're still defining a universal time function such that the branch-like hypersurfaces or the branchial graphs are the level sets of that function. So in other words, what you would see is something like this. So you have a multi-way evolution graph of this form, and then you can, so this is the kind of default choice of foliation, the flat choice of foliation. And then the ideal, the hand wavy idea, which I'll make a bit more precise in a second, is that each state vertex in this multi-way evolution graph corresponds to a different pure state of the universe. So that then when you look at the overall multi-way system and you see the evolution from one branch-like hypersurface to the next, what you're seeing is an evolution from one instantaneous superposition of pure states to another. And therefore the overall multi-way evolution graph in which branch-like hypersurfaces evolve from one time step to the next corresponds to some kind of evolution of a kind of generalized Hartle-Hawking wave function, or a discrete version of a Hartle-Hawking wave function. So if you are interested, by the way, in what I mean by these branch-like hypersurfaces, I mean, this is what they basically are. So these are sort of particular collections of states that this sort of observer is going to treat as being present on the same hypersurface. And so the concept is that if each of these is a different pure state of the universe, then what the observer is actually seeing is some superposition of these pure states, and then in which the magnitudes of the amplitudes are given in terms of path weightings, as I'll show you in a second. So then you'll notice, as well as just showing the instantaneous superpositions, these branchial graphs actually have a bit more structure. They're also showing you, they're also showing certain directed edges between those states. And those are corresponding to ancestry distances. So effectively, a pair of states in a branch-like hypersurface are connected by an edge if and only if the associated states have a common ancestor in the immediate past in the multi-way evolution graph. And so in effect, what these edges are giving you is some kind of discrete approximation to the common ancestry distance in the multi-way evolution. And the reason we do that is because it turns out, again, in certain restricted cases, in particular in the case where the multi-way evolution graph has the structure of an orthomodular lattice, then this discrete, just like in the causal network, the discrete metric on one of these causal graphs sort of limits to the standard spacetime metric in relativity. Here, the discrete metric over one of these branchial graphs in this particularly restricted case limits to the Fubini-Studi metric between pure states in a projective Hilbert space. And of course that's related to Fisher information and to entanglement entropies and all this other kind of stuff. I mean, this is kind of the reason we chose to define it this way is because it seemed to have this sort of fairly immediate connection with the standard, projective Hilbert space way of setting up quantum mechanics. Okay, so let me show you a kind of toy example to illustrate how this idea I just mentioned about relationship between branch-like hypersurfaces and instantaneous superpositions and path weights and amplitudes and all that stuff. Let me show you exactly how that works. So suppose we constructed a multi-way system where the rule is just the application of a square root NOT gate, and where our initial state is going to be a superposition of ket 0 and ket 1. So what we get is a multi-way evolution graph that looks like this. And here we're going to these numbers are showing the vertex weights, and the weightings correspond to path weights. So in other words, down here when we say that the state sort of I0 has a weighting of 4, what that's really telling us is there are 4 independent paths through the multi-way evolution graph that allow us to reach that state from the initial conditions. And so then in this particular case, each instantaneous superposition, each branch-like hypersurface, of which you can see two examples here, is exactly the instantaneous superposition that we would see after applying the square root NOT gate, n number of times. And if you want to, you can go through and check that actually these numbers do work out. You get the right values for the superposition and so on. You get the same result as you would get just by doing the ordinary kind of matrix algebra. Actually, before I move on to that, so we know that this formulation of quantum mechanics works in these particular restricted cases. But so we were interested in this question of can we generalize it to the kind of full hypergraph case, and can we show that there's a particular class of hypergraph systems where the limiting structure that you get from these branchial graphs is actually a standard kind of projective Hilbert space way of thinking about quantum mechanics. And it turns out that proving that was really, really hard in the conventional sort of projective Hilbert space way of doing things. And one of the reasons it was hard was because we had to basically rely on a whole bunch of assumptions about things like monoidal structures that we didn't really have any obvious way of proving. So for instance, as I'll talk about in a minute, this way of formulating things in the general hypergraph case relies on the assumption that if you apply a pair of rewriting rules in parallel, rather than just having a single rule which you apply in places, if you now had 2 rules and you could apply either one, you get some richer multi-way structure. We had based this kind of formulation on the assumption that that was a valid monoidal structure, and that it produced the same kind of tensor product structure as you see in the ordinary tensor product of finite dimensional Hilbert spaces. Now, proving that it's a monoidal structure is actually very easy. I mean, it's actually quite trivial to show that it's symmetric and associative and has left and right identities, as we'll show in a second. But proving that it was the same as the monoidal structure in ordinary sort of finite dimensional quantum mechanics, that we had no real way of doing. So for that reason, we were really excited when we realized that potentially the ZX-Calculus and CQM generally gave us an approach to doing that. That is, we realized that if we could formulate the ZX-Calculus in this context, as one of these, as a sort of generalization of a Wolfram model multi-way system, then we had the possibility of actually proving that that monoidal structure that we based our formulation of quantum mechanics on was the same as the monoidal structure of standard ZX diagrams, and therefore was a valid sort of starting point for the formalism we were developing. Okay, so that's essentially what we did. The first step was to take the rules of the ZX calculus and then sort of reduce them into things into Wolfram model replacement rules. That turned out to not be particularly difficult, although there were a couple of conceptual challenges. One of them is that, of course, the diagrammatic rules of the calculus are they're not kind of finite collections of rules in the conventional sense. So we have generally been dealing with kind of 1 or 2, or at least a finite number of rewriting rules, whereas the ZX calculus defines an infinite collection, because something like the Z spider identity rules, for each possible sort of combination of input and output arities of the spiders, there's a different possible rewriting rule. So we had to, first of all, implement a way of dealing not with particular rules, but with general infinite rule schemas in a finite way. And so we did that, and we came up with a nice kind of automated theorem proving approach to doing that using higher order logic. That's kind of an alternative to the way that software frameworks like Quantumatic use bang box notation for doing the same thing. So here's an example of our software framework allows us to just do kind of systematic enumerations of all possible rules of the ZX calculus. So here's a particular subset of that enumeration. And then, so once the rules had effectively been compiled into Wolfram model multi-way systems, all that remained was to actually evolve one of these things. So that's what we did. So if we start from a single kind of 2-spider initial diagram, we can construct this multi-way evolution graph. So this is the multi-way evolution graph obtained by applying all possible rewrites to an initial diagram of that form. And then that's after 1 step of evolution. If we go to 2 steps of evolution, it quite quickly becomes fairly complicated, and at kind of 3 and above, it starts to become computationally infeasible. But there are some advantages to having sort of formulated the ZX calculus in this framework. So one of them is the ability to make use of the fact that our, as I mentioned at the beginning, our Wolfram model multi-way systems are kind of equipped with a causal structure. So we could start to look not just at the abstract rewriting structure of the calculus, but also at the causal structure. So we could look at here's a particular subgraph of the full multi-way evolution graph for the first two evolution steps in this system. And so here you can see we're showing not just the evolution from one diagram to the next, but also the causal relationships between the rewriting events that allow you to transform from one diagram to the next. If we wanted to, the reason I've shown a subgraph of this is because if I showed you the full graph, which would look like this, it becomes a little bit intractable and it's quite difficult to see what's going on. But actually having this information about causal relationships between rewriting events in the ZX calculus does offer you some fairly useful things when it comes to areas like automatic diagrammatic rewriting and automated theorem proving, as I'll discuss towards the end. But just bear that in mind, that this is a nice sort of feature of the way we've set things up. Okay, so let me now talk about this particular problem that, as I said, the ZX calculus really kind of helped us to solve, which was this problem of identification of an appropriate monoidal structure for our multi-way system framework. So as I mentioned, we've been sort of proceeding on the assumption that when we do parallel composition of rules, then that gives us a monoidal product that is the same as the standard monoidal product of finite dimensional Hilbert spaces. So just to quickly show you how that works, if we imagine sort of two very simple substitution systems, one that says that whose rule is A goes to AB and one whose rule is A goes to BA, and we apply them to a single initial state of AA, then these two different substitution systems will yield these two multi-way evolution graphs that are kind of nice, regular two-dimensional structures. But if we now construct a composite substitution system in which both rules A goes to AB and A goes to BA can be applied and can be applied sort of in parallel, then the multi-way structure we get is now more complicated. It's this higher dimensional structure here, in which the two original two-dimensional multi-way evolution graphs form a kind of spanning set, which is shown, which is highlighted here in red and yellow. And so, and as I say, our conjecture was that this is basically the same as this ought to be morally the same as the standard monoidal product in ordinary quantum mechanics. And of course, this monoidal structure applies not just to multi-way evolution graphs, but also to branchial graphs and all of the other kinds of structures. So if we show, if we consider the branchial graphs in these two cases, we get these kind of very simple one-dimensional objects. After taking this product, then what we get are these two-dimensional objects that are again spanned, as shown on the right, by the original one-dimensional structures. But although, as I say, we can easily prove that this satisfies the axioms of a bilinear operation. I mean, it's obviously symmetric, it's obviously associative because it's basically just a disjoint union of rules. It also fairly obviously has both a left and right identity object because for any multi-way system, you can always just add in a rule that says do nothing. So showing that it contained this particular operation contained the associator and symmetry isomorphisms that a standard monoidal structure should satisfy, that's fairly straightforward. But the question we still had unanswered was, is it the right monoidal structure? Because it's not really clear what this is really doing. It's certainly not taking a standard graph product of the multi-way evolution graphs or the branchial graphs. It's not. This operation doesn't correspond to a straightforward Cartesian product or a Kronecker product or any of these other common monoidal products between graphs. It's related to the Kronecker product, but it has additional sort of mergings between vertices that result from the fact that we're performing state equivalence checking effectively because we're performing isomorphism testing. And so identifying exactly what this operation was and what it corresponded to was not straightforward. But excitingly, the ZX calculus gave us a way of actually addressing that. So because we know in the ZX calculus it's trivial to take monoidal products, you just stack diagrams on top of each other, we now had a way of basically asking, if we take one of our multi-way monoidal products and we take the standard ZX monoidal product, do you necessarily get the same answer? And so that's a concrete question that we can actually address. So what we did was we started from, if we take these are two multi-way evolution graphs that start from the same initial diagram, but they're applying slightly different rules. One is applying the Z spider identity rule, one is applying the X spider identity rule of a particularity. And we get these associated branchial graphs after two steps of evolution. And so then what we could do is, if we applied both of those rules together in parallel, we obtain our kind of standard we obtain a multi-way evolution graph whose structure is given by the standard multi-way monoidal structure, monoidal product of the original two multi-way systems, and it has its sort of combinatorial structure looks like this, and its branchial graph looks like that. But now we can compare that against what would have happened if we'd stuck with a single rewriting rule, say the Z spider identity rule, but instead we'd stacked two ZX diagrams on top of each other and taken the monoidal product in the conventional way. So we could do this. We flip we mutually color invert the two diagrams so that the rewriting rules that apply to one sort of apply to the other, but flipped round, if you see what I mean. And then we can do the same thing. We can evolve this as a multi-way evolution graph. And excitingly, we see up to state equivalence, the multi-way evolution graph we get for this evolution, for which you have a two diagram, one rewrite rule system, is actually isomorphic to the multi-way evolution graph that you get for a single diagram, two rewrite rule evolution. And similarly, the branchial graphs have the same structure. The branchial graphs are also isomorphic to the previous case once you account for these state equivalences. And so obviously this is just a particular one particular case, and we happen to show it because it's a nice illustrative example and it's fairly easy to follow what's going on. But in reality, what we did, we tested this conjecture empirically for several thousand examples of such evolutions of varying levels of complexity, and for all the examples we tried, it seemed to be correct. So it seemed like this was a conjecture that was actually worth proving. And the proof actually basically is more or less a direct extension of the proof that Lucas Dixon and Alex Kissinger gave of the fact that the category of directed cospans of open graphs, of typed open graphs, is a monoidal category. So the way that works, for those of you, I'm sure many of you will be familiar with this argument, but just a quick recap. So so Dixon and Kissinger construct this category of open graphs. So in our I mentioned sort of towards the beginning that in order to be able to simulate the ZX-Calculus in one of our multi-way systems, one thing we had to do was slightly extend our formalism, because we had to, instead of dealing with just hypergraphs, we now had to deal with open hypergraphs, in which we can which we did by just basically marking particular vertices in the hypergraph as being dummy vertices and other vertices as being genuine vertices. The dummy vertices then corresponding to the input and outputs of the diagrams. And Dixon and Kissinger did the same thing. They constructed this category of open graphs that is just like the category that's constructed from a slice category of the category of graphs by marking certain vertices as being dummy vertices and other vertices as being true vertices. And then once that's happened, one can construct the category of directed cospans of open graphs. And Dixon and Kissinger showed that if you take a pair of cospans and you take their coproduct, then that coproduct endows the category of directed cospans with a natural monoidal structure, and therefore the open graphs sort of in a reasonable sense, or at least the directed cospans of the open graphs in a reasonable sense, can be said to form a monoidal category in the ordinary sense. So what we did was to realize that actually Dixon and Kissinger's argument could be extended a little further. So what they had done also in the same paper was to construct these selective adhesive functors that I'd already mentioned that allowed them to get over this problem that the double push-out rewriting rules that one normally applies in the context of graph rewriting which work in the context of adhesive categories, don't work unchanged for the category of open graphs, because the category of open graphs is not adhesive. But what Dixon and Kissinger were able to do was to show that even in the case where you didn't have a strictly adhesive category, you could use these selective adhesive functors to kind of have some sort of quasi-adhesivity condition that allowed you to perform double push-out rewriting in much the same way. And what we realized was that by constructing the category of all selective adhesive rules, selective adhesive double push-out rewriting rules of that kind, we could also construct its directed cospans, and the monoidal structure from the category of directed cospans of open graphs would lift in a very elementary way to the category of directed cospans of selective adhesive rules. And therefore, by taking coproducts of those cospans, we would get a monoidal structure. And so that meant that what we were doing before by doing this parallel application of rewriting rules was really just taking a coproduct of cospans in this category of selective adhesive rewriting rules. And therefore, we could show that it did indeed form a monoidal structure that was furthermore compatible with the dagger structure of the associated dagger-symmetric monoidal category, and therefore was indeed a valid sort of context in which to do quantum mechanics. There are several details that I'm missing out here, including, for instance, what the dagger structure is. I'm sure it won't surprise you to sort of learn that if you take one of our multi-way evolution graphs and you reverse the direction of all the evolution arrows, that involutive transformation does indeed satisfy the axioms of a dagger structure. And with a little bit of extra work, you can show that the dagger structure and the monoidal structure are compatible in the usual way. So this was really exciting for us because it meant that this sort of conjecture that we'd been resting a huge amount of our work on about whether this was actually the same as whether this product that we were using was actually the same as the monoidal structure of finite dimensional Hilbert spaces, using ZX-Calculus and the techniques that Dixon and Kissinger had developed and various other things, we discovered that we were actually able to prove this conjecture, at least in a restricted class of cases. And there are many more sort of examples of places where we hope that actually the stuff that you guys have been developing with ZX will be of great relevance to the kinds of things that we're doing in the kind of in the discrete space-time world, which I think is really exciting. But just because I'm sort of running out of time, and there's a whole one thing I kind of wanted to mention before I wrapped up was I mentioned towards the beginning that I kind of hoped this was the start of a mutually beneficial kind of symbiotic relationship. But what I've said so far kind of makes it sound like it's a bit more parasitic. But just to make it clear that it's not completely parasitic, let me just to finish up, mention some places where I think perhaps the kinds of techniques and ideas and algorithms and formalisms that we've been developing may actually be of relevance to the categorical quantum mechanics world and to the ZX calculus world in particular. So one thing that we've done in the context of the kinds of things that we've been thinking about is to develop a whole suite of automated theorem proving algorithms that I think are pretty sort of highly efficient for doing automated reasoning over these Wolfram model multi-way systems. So for instance, here, this is an automatically generated proof of equivalence between two hypergraphs subject to a particular hypergraph rewriting rule. You can see this particular proof is quite short. It only contains 62 evolution steps. But actually, the theorem proving framework we've been developing can routinely produce proofs that are thousands of steps long in just a few seconds. So it really is quite well optimized. And so effectively what this is doing is it's trying to determine if you specify a particular Wolfram model evolution rule, does there exist a particular directed path in the associated multi-way evolution graph? And this gives you a very, very rapid way of working that out. And so this theorem proving framework is based on a kind of combination of conventional automated theorem proving techniques over equational theories. So particularly things like power modulation techniques for converting between unidirectional rewriting rules and bidirectional equations. And also is based on Knuth-Bendix completion, which is used. So given a particular collection of rewriting rules, they will in general form a non-complement abstract rewriting system. But then you can perform Knuth-Bendix, which will also in general not be strongly normalizing, but you can perform Knuth-Bendix completion by basically adding critical pair lemmas to the system that will eventually turn that system into an equivalent one, which is both strongly normalizing and globally confluent and has the same deductive closure. Those are all kind of fairly standard, automated theorem proving techniques. We also use a few additional optimizations that are kind of physics informed and that are based on the investigation that we've been doing into these discrete models of spacetime. One of which is a new way of basically doing lemma selection. So when you're doing automated reasoning over these kinds of systems, and you want to know, I want to pick lemmas in such a way that they shorten proofs as much as possible. That's kind of the reason for doing lemma selection. Conventional automated theorem proving algorithms may have certain heuristics for doing that, but they're certainly not particularly systematic. But actually, by thinking about things in terms of multi-way systems, we have a different sort of set of intuitions for how that can be done. So given that what we want to do is to select lemmas, select equivalences between states that have the biggest effect on shortening subsequent proofs, one heuristic we can use is by looking at the causal edge density associated to particular evolution paths. So if we look at a multi-way evolution graph, we look at a particular path, we can look at how many causal edges are coming out of that path, how densely causally connected is that path to the rest of the multi-way system. If it's very densely connected, then we can be reasonably confident that if we add that path in as a lemma, it will have a large effect on the shortening of subsequent proofs that make use of it. And similarly, if the path is only very sparsely connected to the rest of the network, we can be reasonably confident that that lemma is not going to be of great use. And so we have a new sort of set of techniques for doing global lemma selection in automated theorem proving algorithms. And in the various examples we've tested it on, it does seem to reduce proof complexity at least quadratically, which is quite a significant saving. And so one question that I think may be of relevance to the kinds of things that the ZX community cares about is whether we can use these kinds of ideas as a new technique for doing kind of automated diagrammatic rewriting for ZX diagrams. So I'm aware that there are various kind of, there's this whole cottage industry of people doing automated rewriting over ZX diagrams with frameworks like Quantumatic and others. But by and large, they seem to be using kind of fairly conventional automated theorem proving techniques, but with some additional kind of categorical magic added. What I think we have the ability maybe to contribute is this new set of ideas that also give us ways of doing efficient diagrammatic rewriting and reducing proof complexity in the process. So in fact, we've developed an automated theorem proving framework for the ZX-Calculus that uses that's kind of building off this multi-way sort of formalism. So here's an example, a rather trivial example of a proof of equivalence between two ZX diagrams. This particular proof only took 18 steps. Again, as I say, we've tested this on proofs of correctness of teleportation protocols and things that have involved several hundred steps, and it seems to be relatively efficient. And at least in the very limited benchmarking that we've done so far, in a large class of cases, we seem to be able to match and in some cases even exceed the performance of frameworks like Quantumatic. And this is by no means, we haven't yet performed a rigorous kind of side-by-side comparison. In fact, that's partly the subject of our follow-up, to our first preprint that's currently in production. But we hope to be able to have that out within the next few weeks, in which we hope to show kind of how this framework can be used as a new and hopefully highly efficient way of doing automated rewriting over ZX diagrams. Another much more speculative. So by the way, I should say that I think that's a fairly kind of near-term practical application of these kinds of techniques. Another much more speculative sort of possible point of common interest between our two camps is in relation to proving things like consistency, soundness, completeness of inference systems. So I mean, Miriam is in this call and knows much more about this than I do, I'm sure. But I mean, proving things about completeness, consistency, soundness of the ZX calculus rules for things like stabilizer quantum mechanics. One of the interesting things about these multi-way systems is that they give you a sort of almost a semi-automated way of doing at least some consistency and completeness proofs. And in fact, we've used this as a technique for doing kind of consistency and completeness proofs over meta-mathematical systems. So obviously, given any axiom system, you can construct its associated multi-way system. And it turns out by investigating certain combinatorial properties of those multi-way systems, you can infer things about whether they correspond, whether the associated axiom systems are complete, consistent, whether the inference rules are sound, and so on. So as a very, very simple example of how that can be done, there are much more sophisticated techniques that we've also developed, but this is just a kind of illustrative example. These are sort of two elementary string substitution systems based on zeros and ones. And in this context, you can think of kind of 1 and 0 being each other's negation. And so then these correspond to particular axiom systems or particular sets of inference rules. And then you can ask, do they correspond, are the associated axioms complete? Are they consistent? So this multi-way system on the left here is an incomplete one because there are certain strings like the string 111 where the system doesn't generate that string, but it also doesn't generate the negation 000. On the other hand, on the right, there's an example of a multi-way system that's inconsistent because there are certain strings like 010 where in the multi-way system there are nodes that correspond both to 010 and its negation 101. But as a happy balance between the two, there are some multi-way systems which are provably guaranteed to generate, for any given string, it will generate either that string or its negation, but never both. And those are the multi-way systems which are therefore provably both, where the underlying axiom system is provably both complete and consistent. So we've developed, again, a collection of automated techniques for doing essentially completeness and consistency proofs over multi-way systems that we're sort of cautiously optimistic might be useful as a kind of as a general technique for doing completeness and consistency proofs over ZX and related calculi, particularly things like ZW and ZH and other kind of similar diagrammatic rewriting systems for which there are open questions about whether they correspond to sound, complete, consistent axiommatizations of stabilizer quantum mechanics and things like that. Like I say, this is a much more kind of speculative angle, but it's another place where I think potentially our two ways of thinking about things have the potential for sort of mutual benefit. Anyway, so I've probably spoken for long enough now. I've gone on for 50 minutes or so. I'd love to have some time for questions. Just quickly before I finish, I should mention that the code that I've shown here, all of this is kind of freely available. It's all open source. You can download it from the Wolfram function repository. And if you want to find out more about the project and about the kinds of stuff we're doing or links to our various preprints, you can visit our website over here. But anyway, I'll stop talking and I should take some questions.
Let's thank the speaker. So does anyone have any questions?
I've essentially got an enormous amount of questions. So basically, can I email you?
Yes, no, please do. Please do.
Fantastic. I've been working on quantumatic and automated reasoning and conjecture synthesis. So hopefully we'll have some things to talk about.
That sounds wonderful. Yeah. Do you have so many that it's not fruitful for us to talk now, or?
I fear so. I don't have enough of a physics background that I need to go over some things with you just to check and things like that. So thank you.
Okay, fair enough.
Can I ask a question?
Yes, please.
Yeah, so just wondering. So can you have you heard about algebraic ZX-Calculus, which basically has a triangle as node as a new generator?
Sorry, I missed the first word. Which variant of the ZX-Calculus?
The algebraic.
Oh, algebraic.
So which
Okay,
has
yeah. So please go on.
Which has a triangle node as a new generator.
Mm-hmm.
So I just wondering, is it possible to realize this style of ZX in your system?
Yes. So okay. First of all, I should say I've heard of algebraic ZX, but I'm not an expert on it. I think I've read one preprint on it a while ago. So to the best of my knowledge, if it's only a case of adding an additional generator, basically if you're just adding an additional kind of spider, then there's no barrier, there's no obstruction to you being able to simulate it using one of these multiway systems. Basically as long as it can be formulated in terms of double push-out rewritings over the category of open hypergraphs, then I think you can do it.
But the problem is because the triangle node is a kind of a directional. So Hector before has suggested to put the red pi to combine with the triangle, then it's directional. So I mean, so in your system, is it possible to have a more simpler way to do that?
That's a good question. So, okay, correct me if I'm wrong. Can I essentially rephrase that as, is there a simple way of having kind of a mixture of directed and undirected hyperedges in one of these rewritings?
Kind of.
Yeah, okay. It's an interesting question. It's something we've thought a bit about. We don't, we experimented with it a bit. We don't really have a full underlying theory about it. Basically, when you formulate one of these hypergraphs in terms of these collections of abstract relations, whether those relations are ordered or orderless is kind of arbitrary. So in the way we've set things up, you can have mixtures of ordered and orderless relations in the same collection. There's no restriction, there's no issue with that. And obviously the ordered case gives you effectively directed hyperedges. The orderless case gives you effectively undirected ones. Whether that would give you a more elegant way of representing these triangular generators in algebraic ZX, I don't know. That's a really interesting question. I'd love to discuss more about it. Maybe that's one of the many things that Hector and I can talk about later.
Okay, thank you.
But no, thanks. I didn't know about that. Thank you. That's good to know.
I have a question.
Please, yeah.
You talk about this multi-way monodal product. Maybe I wasn't just paying attention, close enough attention, but in what category?
So it's right. It's over a category that we have constructed of these multi-way evolution graphs. So we in the preprint, I didn't go into all the details here, but in the preprint we essentially construct implicitly these categories of multi-way evolution graphs and branchial graphs. And so each one is associated to a particular rewriting system, a particular initial condition, and a particular step number. And then we can take monoidal products over over those categories. We can enrich those categories with monoidal products, and that's the structure I was referring to.
Okay.
And so in effect, what they are just certain subcategories of the category of graphs, at least in simple cases.
Okay, thanks.
It's okay.
So, hi, can you hear me?
Hi, yeah, you're a little bit quiet, but
better now?
Yes, much better.
So a follow up on Cole's question. So something I didn't pick up quite well was that you were trying to, well, one of the things that you were trying to do was to show that in some way these monoidal products on your structures were related to the monoidal products on vector spaces.
Well, that's that what we get is a dagger-symmetric monoidal category of the same kind as you get in the category of finite dimensional Hilbert spaces.
Right, but the thing, like the reason I'm asking is that I felt it was surprising. Maybe I just didn't understand what you were trying to say, but I felt it was surprising because the monoidal product that you're showing, at least the way I understood it, looked very much like a categorical product, so like something similar to a Cartesian product. And in the case of vector spaces, you have something that has way more in the object. You have way more vectors than just a pair of vectors. So I was wondering if that's something that you also want to take care of, and if it's something that is relevant for you, and if you believe that it's also solved with your approach.
Okay, yeah, that's a good point. So what we have is, it's important to say that what we have is not a Cartesian product, but it's also not a Kronecker product. It's something else. It's some kind of modification to a Kronecker product with additional state equivalences. So yeah, it's certainly true that if you had no merging criterion, then what you would get when you took one of these products when you took one of these multi-way monoidal products of say branchial graphs would be exactly a graph Cartesian product. And if you were just looking at the graph structure, I agree, of course, that that it would be absurd to claim that that was in any way related to a product of finite dimensional Hilbert spaces. But the point is that if each branchial graph is denoting an instantaneous superposition, such that every subgraph yields a different, essentially yields a different vector in the associated projective Hilbert space, then what you need to be thinking about is not the growth rate in the number of nodes of the graph, but the growth rate in the number of subgraphs. And that grows with the same scaling relation that you would expect from the ordinary finite dimensional Hilbert space product.
Okay, that makes more sense.
Yeah, I agree. If it were the case that you were claiming every vertex were a vector, then yeah, you would have an immediate sort of counting problem.
Okay, thank you.
But no, it's a good question. It's something I didn't make very clear, but thanks.
Hey, I have a question.
Please, yeah.
Thanks for the talk, first of all.
Thank you.
So did I understand correctly that given some initial graph and some rewrite rules that you decide, then you just run the algorithm, let's say, and you generate every possible future of rewrites, and then from that you build a manifold? That was like on the first part of the talk, the more physicsy. And then
right.
And then you can see like invariants under you can see symmetries, like rewrite symmetries, and that gives you like Lorentz invariants and stuff like that, which is really cool. So, but then when you switch to ZX, you said it's too complicated to even go to step 3, right? So you have no idea what kind of manifold you get from ZX?
Right. Okay. Really good question. So the even in the hypergraph case, for beyond about 20 evolution steps or something, it becomes completely computationally intractable if you want to run the whole evolution tree. So in reality, we don't do that. What we look at, because most of the geometrical structures we care about are not, well, one thing is causal invariance means that in some sense, you don't have to populate the whole tree. If you only care about the causal structure of the rewriting events, then you can get away with just following a particular evolution path, and you can kind of ignore all of the others. And because it's causal invariant, that the causal network you get on that path will be the same as as you would have got on all the other paths. So even in the hypergraph case, we have to make that optimization. It just happens to be the case that for the full ZX calculus, the need to make that optimization is even stronger because of the fact that rather than just having a finite set of rules, you have this infinite, you have a finite set of infinite rule schemas. The multi-way evolution graphs tend to grow much more rapidly. But it is the case that we have the ability to investigate essentially what the limiting manifold structure is for ZX calculus rewritings for particular evolution histories or particular evaluation strategies. And because the ZX calculus is, well, depending on exactly how you formulate it, because it's causal invariant, or at least can be made into a causal invariant theory with the same deductive closure, that optimization is still a valid one to make. And so it's not something we've investigated in much detail, but it is something we definitely plan to look at, is basically what is the limiting geometry of ZX calculus rewritings.
Okay, I see. That's very interesting. And then you would expect that any complete calculus, like okay, let's say it another way. So ZX is as powerful as ZH in the sense that they can represent all linear maps. They're both complete, for example. But sometimes it's better to use one rather than the other, depending on the application, right? So, and then there's some work which I'm not very familiar with, that there is not an infinite family of Z something calculi. There's ZX, ZH, ZW, and then the community calls all of them collectively Z star. So I'm wondering if you ever do this with the manifolds, and you see what physics arises, will you see a difference if you use either of them, or if you use all of them at the same time? Like, I don't know.
Right. No, that's a really interesting question. So what we would expect is, okay, in the case where you have two multi-way systems that have the same expressive power, which is the case, I believe, with, as you say, with ZX and ZW and so on, then what you would expect is to see that the manifold structure you would get, or the causal networks you would get, are conformal rescalings of each other, or actually, depending on exactly how you set it up, they might also be quasi-conformal rescalings of each other. So when you say that there are some classes of problems for which ZX is a more effective tool than ZW or something, translated into our context, what that's really saying is that you can always reach the same states in the multi-way system, but the paths you needed to reach there can vary. And so then when you look at the associated causal graphs for those different paths, you're stretching and scaling certain parts of the manifold, but you're not actually changing the topological structure. So what you expect is that the manifolds are all equivalent up to some quasi-conformal diffeomorphism. And actually, we've investigated that in the broader context of computational complexity theory. So we looked at, this was several months ago now, but we looked at in a completely different context, looking at basically the limiting geometry of non-deterministic Turing machines, and then looking at different ways of setting up non-deterministic Turing machines. And yeah, exactly, you discover basically that different complexity classes, but with the same computability class, correspond to different sort of quasi-conformal diffeomorphisms of the same manifold. And we should expect to see a similar thing here. But yeah, it's an exciting thing to figure out.
Thanks.
I've just realized that I do have a fairly easy to ask question. All right. So for you mentioned comparing quantumatics automated proving with your own. When you say quantumatics automated proving, is that like the Python interpreter built inside Quantumatic?
Yes.
Okay. Have you looked at physics, which is not done by me, but it's by Alex and John. It's essentially a standalone version of that, which is its own Python environment, which may massively improve any sort of testing you're doing.
I hadn't heard of that, but please do send me details. That's
I'll do that in an email.
That'd be very useful. But so are you saying that there's that's a way of sort of essentially reducing system overhead?
Yes.
Okay.
I don't know if they are entirely this. I haven't played around with it enough to know if you'll get like precisely the same results if you put something into Quantumatic as into physics, regardless of time, whether it has the same accessibility. But physics was designed to be a freestanding version of that same Quantumatic functionality.
Okay, that sounds eminently relevant. Thank you. I didn't know about this. Hopefully, it shouldn't affect the validity of the analyses we've done so far, because we were looking at complexity classes and scalings rather than absolute times. But that's it'd be useful to look into.
It will just allow you to automate more of it, I suspect.
Yeah, right. Which we definitely want to do. Thank you.
Well, we appear to have lost Cole. So as sort of ex-chair, thank you again. That was a fascinating talk, especially given that it was further away from what we usually talk about than normal.
Well, I'm sorry that sorry if it was a little bit out of left field, but yeah, thanks very much for inviting me. It was great to be here. Okay, so I should probably let people go, but yeah, please feel free to email me, any of you. But yeah, Hector in particular, if you have useful things to send my way, please do get in touch.
I will. Goodbye.
Thanks.
Thank you.
Cheers.